Good day, everyone. So one of the AI/ML techniques is artificial neural networks. So where the inspiration is from real biological nerve cells. Biological nerve cells have multiple dendrites as inputs. There might be thousands or more inputs to a single nerve cell. The single nerve cell takes all those inputs and makes a decision, and the axon is the output. Axon is a single output, but then there are multiple terminals. Those terminals may feed to other dendrites and in turn feed to other nerve cells. So from this we have taken an inspiration, and this one line explanation is already simplified. The nerve cell is much more complex than that, but basically artificial neurons actually do a much simplified model where there are n number of inputs. Here in this example it is 4. There is a weighted summation, and the weighted summation, let's call it S sigma wixi. So yeah, S is the weighted summation, and that's fed into a function. This function actually outputs a y, which represents the outputs of the output of the nerve cell, and there are multiple billions of such units that are connected together, and that is part of how the deep learning networks or the artificial neural networks are structured. So the different ways in which the multiple nerve cells can be connected, there are different functions that we could use. There are different ways in which we handle the inputs. There are different ways in which we handle the weights, but still actually the fundamental model has remained the same for many decades now. Okay, let us take this example problem here. So there is a interview process. The interviewers are evaluating the candidates on 2 dimensions, skills and attitude. The scoring is between 0 and 5. And we have the data set of previous decisions that has been made. The data set here is very small. There are 3 candidates and their scores and the decision. So a selected value of 0 means they were not hired, and a selected value of 1 means they were hired. So this is a simple exercise. So we will use this to understand so some matrix operations on Numpy more specifically, and also this idea of this weighted summation to make a decision. So there are 2 inputs. Skill and attitude are the 2 inputs. We do a weighted sum. And then there is the function here. The function here is if the weighted sum is greater than a threshold, then the overall output of selected or not selected needs to be 1. If it is less than that threshold, it is basically needs to be 0, and the decision is not hired. So this is the problem, and basically we can see that the weighted summation is exactly the same. We do a linear weighted summation. So f of s is basically the check that we are doing. The particular example that we are having here, the example function that we are having here is discrete. It is non-continuous. So it is a step function. We don't use that in today's artificial neural networks and deep learning networks. The learning is one of the things that we want to do. Having a continuous function allows us to use calculus. And using calculus, we are able to adjust these parameters, the W values. When we that is how the learning happens, and for that actually using continuous functions is important. So here actually there is a small data set of 3. So let us introduce the variables. Y is the overall output, which is the selected or the not selected decision criteria that is there. X is the input data set. So this is actually 1, 3, 3. So that is the first row. 1, 3, 3. So this first row is corresponds to the skill scores in our data set. The second row corresponds to the attitude scores in our data set. Y is actually a 1 cross 3 matrix here, 0, 0, 1. So that is basically our final decision. Okay, y equal to W transpose x. So W is actually W1, W2, which is a vector, which is the parameter vector. And X is what we have on the screen here. So basically we can see the order of the matrix to confirm that this operation is correct. So that when we deal with matrices, that is something that we helps us basically. So W transpose will be 1 cross D. I'm going to introduce D here. D is the number of dimensions, the skill and the attitude, or the number of parameters. So I'm going to call the number of parameters D. So W is a W transpose will actually be a horizontal matrix with one row. So it will be 1 cross D. And the X actually we can see it is, there are D rows here, and the N is the data set length. So it is actually a D cross N. So when we do this multiplication, we actually get a 1 cross n, and that is exactly the y that we have see here. That actually gives us a confirmation that this operation that we have here makes sense. What we want is w. So this is what we are going to code up in Numpy just now. So y equal to w transpose, we are doing a few matrix operations here. What we are doing is multiplying on both sides by x transpose. Then actually we are taking a transpose of the left side as well as the right side. So we are doing this transpose equality on both the left side and the right side. So to convert that into xy transpose, xx transpose actually happens to be the same as its transpose. It's a symmetric, xx transpose becomes symmetric. So by bringing over xx transpose to the other side, it will become an inverse. And this is what we will try to solve. X itself is not a square matrix here. However, xx transpose is a square and a symmetric matrix here. So the inverse operation is possible. So I've moved to a new screen. So we are going to type some code in the terminal window here, but we are also going to keep the handwritten notes at the top for reference. So it we need the equation here for calculating the weights using the closed form equation, as well as we need the example input values that we have, the example data set that we have taken, right? So before even we start typing up the code, two things. So one is basically we are doing an xx transpose inverse here. Not always xx transpose may be inversible. The determinant needs to be 0. So the condition is the rows of x. In this case, actually, we have arranged it as d cross n. D is the number of features in the input, and n is the number of samples. So the samples are arranged in columns, and the features, skills and attitude are arranged in rows. So the rows need to be linearly independent. If that condition is met, then xx transpose is inversible. The rank needs to be at least the row rank. That is the condition that we have. So D cross N, N cross D is the shape. So one of the things that is very essential for AML practitioners is to look at the shape of the variables that we use. So we do it's be good to actually put a code command against each of the variables with the shape, so that we can while coding itself we are able to see if the operation that we are doing is making sense. Right, we know that basically D cross N matrix multiplied with N cross D is a valid operation. So that is what is happening here. So the second part, before even we go start typing code, let's actually open Python in interactive mode and type some Numpy code, right, and try out some Numpy, right? Import Numpy as np. Yeah, this is a common practice to import it using the alias np. You will see this in quite a few code out there. So the screen has x, which is the example input that we had used. So for creating a matrix like this in Numpy, what we would do is use this numpy.array. So that is how we would go about creating a matrix in Numpy. Then let's actually look at a few more interesting things. X dot t. X dot t is a transpose operator. The dot t is a transpose operator. And we also need to do matrix multiplications, right? So here we have x and x transpose here. So the way we would do that is x dot t, and this at operator is a matrix multiplication operator. So that is the convenience that we have. So one more the thing, next step is inverse operation, right? So for inverse, we have np.linalg. Linear algebra utilities are present here in linalg. Inverse is one such. So x at x3. So that gives us computes the inverse. Then actually there are, in these variables, there are member variables which are actually useful. For example, this is a two-dimensional matrix. ndim gives you the dimensions. This is the number of elements. The size, x dot size, gives you the number of elements. Shape is another useful, more useful data member that we have. 2, 3 is the shape. Row, column, it's the usual matrix convention. We have 2 rows and 3 columns. So it's actually fairly straightforward to ramp up on Numpy, and there is actually a GitHub hosted web page, the link in the description below. There is a learning page with 10 slides and also a speed game. So I will encourage interested users to try it out. So let's now that we actually get a feel for what Numpy is used for, let's go ahead and type the closed form solution. I'm actually doing the same thing here, bringing the x variable first. In addition, let me actually make it explicitly a float32 data type. So the way we actually can select a data type is using this d type argument that we can pass in to np.array. Key value pair that we can pass. D type is a valid key value pair that we can pass. We are passing it with the np.float32. Np, the package actually has the many different data types like float32, float16, int32, int16, and more, right? So proceeding, we also need the y. Y is actually, I'll make it yc. This is actually the dataset target values that we have. I'll call it yc. Y with a cap on top is what why I named it as yc. That is our target values. So we saw that we can do we are going to do this, calculate w first, and let's do that step by step. We need x transpose. X.3 gives us x transpose, and we saw in the interactive session that basically x at x transpose is a matrix multiplication. So x transpose can be done like this. So xxt is another variable that we will create for this, and also we want the xxt inverse, which we can do using np.linalg.inv. This gives us the inverse. Then let's go ahead and actually compute the weights using this closed form expression, which is basically x and yc.t, y transpose. Yc is the variable that I have taken, right? So before we proceed further, let's just print the inputs and the weights so that we can inspect. Variable naming, let me fix that. Okay, so the weights that we are getting is 0.1 and 0.05. So based on this data set, we are using a closed form equation. We are calculating the weights to use as 0.1 for skill and 0.05 for attitude. That is, this data set we have assessed to be using the weights that we have found. So now we can actually use the same set of weights to find the result for a new candidate, for evaluating a new candidate. So let's actually go to that next step. So I'm going to take a new n for the new candidate, np dot array, and let the new candidate have actually scored 4 on skill and 4 on attitude, and let's see what happens. So the yes value that is for the result will be basically y transpose and the new input. I used a variable s because basically the threshold value, right? We also need to do a threshold value there. So s greater than, let me use a threshold value like this and make this y uh, selection result and print all of these. Weighted sum of scores is yes. Okay, let's actually double check the sizes here. W basically is 1 cross D. And actually single dimensional arrays NP automatically takes. So both of these are 2 basically. So we are all right actually. So one of the n will be in typical mathematical convention we use vectors. So it will be basically 2 comma 1, 2 rows and 1 column for n, and W transpose will be basically 1 comma D. 1 row and D columns, because we have done the transpose operation. W also is a vector, and since we have done the transpose operation, and basically even if we ignore the fact that NP for single dimensional arrays, it automatically handles this, the shapes are matching. So we do expect this to work correctly. Okay, the decision is true. This particular candidate got selected. Congratulations. So and let us actually and take another example as 2 comma 2. And unfortunately, this candidate with scores of 2 comma 2 did not get selected. So this is to basically get a feel for what we are actually doing. This is one example. There is another popular example using for the gates, right? And or NAND, NOR. So it is possible to construct a similar weighted addition and a threshold type of solution for actually implementing using a single artificial neuron gates like and or. Yeah, good number of the basic gates are implementable, but basically gates like XOR are not implementable. That's for some other day, but maybe interested users can think about it more. Thank you. In the next video, we will go back to math. We are going to look at gradients, calculus. So that is what is our plan for the next video. Thank you.